basically what we're going to be going over here is the normal distribution. The homework involves some calculations involving the samples and confidence intervals. It involves the use of, in a few instances, not so many, but in a few instances, t-scores instead of z-scores. Although, for the most part, I made the sample sizes pretty large, so that doesn't come up too often. But we'll try and see if we can't figure out like when we're going to apply all of these different things. And that's really kind of like the hardest part of this whole thing is when do we apply certain rules and what are our assumptions that we're making as we go through this. So I'm going to start with example number 1. Sample of size 160 has a mean of 160. We don't know what the units are here. It doesn't really matter. Assuming the population is normally distributed with standard deviation sigma equals 30. Okay, so first thing I see here is we have a sample. Sample has a size of 100, has a mean of 160. In this case, we know the standard deviation of the population. We know what sigma is. Remember that sigma, Greek letter, represents a parameter, meaning that we know that it's a population measurement, not a sample measurement. So sigma is equal to 30. X bar is a sample mean, right? Because we're using the letter X instead of using the Greek letter mu. Okay, so first question we got is compute a 95% confidence interval for the true mean of the population. In other words, for mu, we know what X bar is for our sample of 100. We don't know what the population standard deviation is. And in most cases, we never know what the true population standard mean is, right? We have to rely on our guess, the mean that we get for our sample and our confidence interval to help us with that. So I already kind of started to lay this out. So we know we have sample size of 100, mean is 160, standard deviation population. So we know first thing we're going to have to do is calculate a standard error. Our standard error is going to be equal to sigma over the square root of the sample size, and that's going to be equal to 30 divided by the square root of 100 is 10, so it's going to be equal to 3. And we know our confidence interval is going to be the mean plus or minus. In this case, since we know the population standard deviation, we're going to use the value for z for a 95% confidence interval, right? 95% confidence interval, and also an alpha error, possibility of an alpha error of 0.05 or less, right? So we're going to use 1.96, okay, times the standard error, which in this case, the standard error happens to be 3. Okay, so times 3. Okay, I'm going to round this to, well, let's go ahead and do this actual example. Okay, so that we have the actual answers that we need. Okay, so it's going to be, I'm going to clear this, 1.96 times 3 is equal to 5.88. I'm going to put that into memory. And our mean again was 160. So clear that, 160 minus our margin of error, 154.12. Right? And the upper limit for our confidence interval is going to be, I'm going to clear that, it's going to be 160 plus our margin of error. It's going to be 165.88. Okay, so I'll put that aside for a moment and let's take a look at the next part here. If instead the population mean were known to be 95%, if instead the population mean were known to be mu is equal to 160, what would be the probability that a single observation selected at random from the population would have a value of less than 154? Well, what we're assuming there is that we know that mu is equal to 160, and we know the standard deviation is equal to 30. So we just fell back into our knowledge of the normal standard distribution. If the mean is 160, right, and we're looking for the probability that we get a value less than 154, that's the area of this distribution below 154, right? That area below here. That's going to be the probability that we'll pick somebody out that's under 154 from this normal distribution. Well, in order to figure out what that area is, we have to calculate the z-score. Z-score is equal to whatever the value is, x minus mu over the standard deviation, which is equal to 154 minus 160 over 30 is equal to 6 over 30, okay, which is equal to 1 over 5, if I'm correct, which is equal to 0.20, negative 0.20. Okay, so what is that area going to represent? What is that area that's going to be represented there? Okay, well, I can go to my t table, my z table, excuse me. Oops. And look for a z-score. Whoops. No, got the wrong page here. Let's go back here. My z-score of negative 0.2 is going to be 42%, 0.4207. That area is going to be equal to 0.4207. So the probability that we would pick out an individual that has a value below 154 from this population is 0.4207. Okay, or about 42.07%. Okay, let's see the next part here. For the scenario B, what is the probability a single observation has a value greater than 166? Well, now we're 6 above the mean, right? So this area is going to be symmetrical to this area, so it's also going to be 0.4207. Okay, so I really don't even have to go back to the table for that. For the scenario B, what is the probability that a single observation has a value between those two? Well, we know if we're looking between those two, we got 42% here, 42% here, and that's going to leave us with approximately, right? What do we have there? 42, that's going to be 84%. That's going to be approximately 16%, 0.16, right? Probability of picking someone out between those two values is going to be about 0.16. Actually going to be 0.1584, it looks like. Okay, if I do it exactly. I think you probably agree with that. Everybody agree with me on that? Are we okay on that particular problem? Okay, a little bit of a switch there, right? We first, in the beginning, we would look at confidence intervals, and then we went back and we looked at what that distribution would look like if we happen to know both the standard deviation and the mean. Everybody comfortable with that? Okay, I don't see any comments, so I'm going to assume that we're okay with that and move on to the next one. Okay, after observing 25 randomly selected caseworkers, supervisors noticed that the average number of cases carried by each worker in a week was 50. So our average number of cases is 50. From a previous long-term observation, it is known that the standard deviation for the entire department is 9 cases per week. So we have a known standard deviation for all of the caseworkers, which is 9. Sigma is equal to 9. Our mean number of cases is 50, and we got that 50 from a random selection of 25 caseworkers. So n is 25, x bar is 50, and sigma is 9. Calculating 95% confidence for the mean number of cases per caseworker per week for the entire department. Okay, we think it's going to be around 50 because that's the mean that we got when we randomly selected 25 workers. 25 caseworkers, but we don't. We know that's our sample means. So we know that's not going to be necessarily a population mean. But now we want a confidence interval for a population mean. So let's see how we're going to handle this. We already have sample size. I got x bar, and I have sigma is equal to 9. Since we have sigma is equal to 9, we know that when we calculate our confidence interval, we're going to be using a z-score of 1.96. So we're going to have, let's first calculate our standard error. Our standard error is going to be equal to sigma over the square root of the sample size, which is going to be 9 over 5, right? Square root of 25 is 5. That's going to be equal to 1.8. That's our sigma. So now to calculate our confidence interval, we have x bar plus or minus 1.96 times our standard error, which is 1.8. Okay, well, let's go ahead and let's calculate that. And our mean is, we know, is 50. 50 plus or minus 1.96 times 1.8. So let's get a calculator out and let's clear things out again. And we have 1.96 times 1.8 is equal to a margin of error of 3.528. Remember, this part is called our margin of error, right? And I'm going to put that into memory. And I'm going to say 50 minus our margin of error is going to be equal to 46.747. Okay, so it's going to be 46.47, right? Yep, I'm going to drop off that last decimal place for our purposes. Okay, and then I'm going to try adding it to it as well. So clear that out. 50 plus our margin of error. Okay, it's going to be 53.53. Right, and I think I got that right. Yep. Okay, so when we sample 25 caseworkers, we get a mean of 50 cases completed per week. That's very nice, but we don't have a way to measure how likely it is that that's really going to be our mean. So instead, we calculate a confidence interval. So we're 95, based on what we know about this population standard deviation and the mean that we got from a sample of 25 people in that sample size. We estimate that our 95% confidence interval says that we're 95% certain that the true mean of the number of cases performed each week by these caseworkers is between 46.47 and 53.53. Okay, let's take a look at the next part of this problem. Calculate a 90% confidence interval for this population. And how about a 99% confidence interval? Well, we know what we're going to do then is, instead of using 1.96 for a 90%, a 90% confidence interval, we are instead going to say 50 plus or minus. Instead of 1.96, we're going to say 1.64 times our standard error of 1.8. Right? That's going to make our margin of error smaller, since it's going to be a smaller number here, right? So that means that we're going to have a narrower confidence interval. It's going to be closer to 50 on both the low end and the high end. So since it's narrower, we have less confidence. So we're only 90% confident. If we want to be 99% confident, well, it's going to be a wider interval that we're going to wind up with. The wider it is, the more confident that the true mean is going to be between. We're not going to miss the true mean, and that will be between. That's going to be 50 plus or minus 2.58, and we know that this 1.64 and the 2.58 are coming from our z table times 1.8. Okay, I'm not going to bother to work out the actual numbers for the 90%, 99%. I'll leave that up to you guys, but I think you should be able to get through with that. Okay, let's take a look at number 3. Okay, number 3. Suppose we would like to estimate the mean amount of money, mu, spent on books by Hunter students in a semester. We don't know mu, we want to estimate it. We have the following data from 100 randomly selected Hunter students. The mean amount spent was $249. The standard deviation was $30. Now notice that we use the letter S for standard deviation. That means we're taking that standard deviation from the 100 students that we selected. We calculated standard deviation for the sample, not for the population. So now this is an application we're going to have to use a t-score instead of using a z-score. Now it happens to be a large sample size, right? 100 is a pretty large sample size. So that's going to impact this again a bit. So let's take a look at how it might impact it. Okay, assume that 30 is good. Well, actually, in the next part it says, assume that 30 is a good approximation of standard deviation for all students. In other words, assume it's asking you in the example to assume that the 30 is also the population standard deviation, so that you know sigma. Well, I'm going to kind of work this a little both ways so that we can see how we might deal with this. Okay, so I'm going to say, okay, let's see. In this case, sample size is 100, mean is 249. Standard deviation, which we're assuming to be the same as sigma for our purposes. And one of the reasons we might do that is because the sample size is so large. We might say, let's make that assumption that we accurately estimated the standard deviation and that we know sigma, so that we can use the z-score instead of having to use the t-table. Okay, so just like before, if we want a 95% confidence interval, we would estimate that by saying, okay, x bar plus or minus the z-score for 0.05, right, 1.96 times the standard error. Okay, which in this case is going to be $249 plus or minus, okay, since we're going to assume we know sigma, 1.96 plus or minus 1.96 times our standard error. Now, what's our standard error? Well, a standard error is going to be equal to our standard sigma, or a sigma, standard deviation, 30 over the square root of the sample size, which is 10. Okay, which is going to be equal to 3, just like we had before. Okay, so we're going to wind up with a confidence interval, 95% confidence interval of, let's go ahead and work this out. Okay, is going to be 1.96. Oops, let me clear that. 1.96 times 3. And I'm going to put that into memory. And I'm going to clear that out, and I'm going to say 249 minus margin of error is 243.12. 243.12. And the upper limit for our confidence interval is going to be 249 plus our margin of error, which is going to be 254.88. Okay, now let's say we didn't make this assumption, that we didn't want to say that the sample size is good enough, this big sample size is good enough for us to assume that we knew that sigma was equal to 30. Let's say for a moment we didn't want to make that assumption. Well, then we would have solved x bar plus or minus, right? Instead of using the z-score, we would use the t-score for alpha is equal to 0.05, right? And for a sample size of 100, or number of degrees of freedom 99, right? Whatever that t-score is, and we're going to multiply that times our standard error, which happened to be 3. Well, let's look up our t-table and see how that would affect things. Okay, let's get our t-table. Okay, so we got our t-table. So let's go to 99. Well, closest I got is 100. So if I look for my t-score, the t-score I need to use for a 95% confidence interval, in other words, 2.5% in either tail, that would have to be a t-score of 1.984. So that would be 1.984. So x bar plus or minus, right, 1.984 times our standard error of 3. In other words, this would be 249 plus or minus 1.984 times 3. Well, what effect did this have? This had the effect of having us use 1.984 instead of 1.96. Almost the same value, right? That's why in a lot of exercises, especially preliminary calculations, we're willing to make that leap of faith and say that, let's say we know the standard deviation and we're going to use the z-score of 1.96 for our initial calculations. But the more correct way is to use the 1.984. That's a more accurate confidence interval for this situation. Okay, so actually let's go ahead and calculate it, see how different it comes up. Okay, so I'm going to go here to my calculator. and clear memory again. Okay, and I'll clear this. So it's going to be 1.984 times 3, our standard error. Okay, and now that's going to be on my margin of error. Whoops. 1.984 times 3. And I'll put that into my margin of error. Okay, I'll clear. And 249 minus our new margin of error equals 243.05. 243.05. Notice it's a little bit wider, right? Because now I'm accounting for that. I am accounting for that extra uncertainty because even though it's a big sample, I don't really know for sure what the population standard deviation is. And for the upper limit, it's going to be 249 plus our margin of error, 254.95. 254.95. So you'll notice that it's just a little bit different, right? But if we used SPSS or some statistical software, it would always use the t-score. For convenience, sometimes we'll wind up not using the t-score. Okay, so let me see. I want to stop at that point because I want to see if you guys have questions about this. Okay, use the z-score in these situations as opposed to the t-score. Well, in this problem, for sure, because I even encouraged you to do it in the problem. I mentioned it. Okay, we weren't really given the population standard deviation. You were told you can go ahead and make the assumption that it's the same as the sample standard deviation. So you weren't really specifically given it. If you were really given the population standard deviation, then by all means, you should go ahead and use the z-score instead of the t-score. But for any situation where you don't know the population standard deviation, the more correct way is to use the t-score. However, if it's a large sample, and by a large sample, a lot of times we define that as anything that's bigger than, say, a sample size of around 30 or something like that. You can go ahead and use the z-score, but perhaps it'd be best to mention that you're using the z-score with the presumption that the sample size is large enough for you to not use the t-score. So you might want to mention in your answer. Okay, so if we're told to assume standard deviation is the same, we can use the z-score. Yes, that's absolutely correct. In fact, you should use the z-score, because if you don't use the z-score, then you're kind of punishing yourself because you use the t-score to make up for the uncertainty that's introduced by not knowing what the population standard deviation. It's actually a more conservative approach to use the t-score, even if you know the population standard deviation. But you don't need to. So why punish yourself? Why not make it so that you can have a narrower confidence interval if you have the right to do it, since you know the population standard deviation. So in general, make a long story short, if you know the population standard deviation, use the z-score. If you don't know the population standard deviation and it's a large sample size, you can go ahead and use the z-score instead of the t-score. If it's a small sample size and you don't know the population standard deviation, then you have to absolutely use the t-score. Okay, so we can use yes. Okay, yes, even if the sample size is small, because that adjustment to the t-score is really based on the fact that you're estimating the population standard deviation based on a sample, so you don't really know what it is, right? Just like you don't know what the mean is, for sure. If you know only the sample mean, you don't know what the population standard deviation is if you're only basing it on the standard deviation of a sample that you took. So that's really what's governing this whole thing. Okay, so yeah, you can use, even if the sample size is small, you can use 1.96. Okay, so let's go back and let me take a quick look at this. Okay, and the rest of this problem was calculate a 90% confidence interval, and for, again, if we were going to use sigma, we would use the number. If we were going to assume we knew sigma, we would use 1.64 for our z-score, and for 99% we use 2.58. Now, if this were a small sample size for 90%, we would have to go to our t-table again. And on our t-table, like for instance 100, our t-table for 90% confidence interval, we would use a t-value 1.66 instead of 1.64. And for a 99% confidence interval, instead of 2.58, we would use the value 2.63 or 2.626 instead of 2.58. Okay, so again, sample size determines whether you have to go to this table for the 95%, 90%, or 99% confidence interval if you don't know the population standard deviation. Okay, again though, look how close these are when you get to a sample size that big. That's your real justification for kind of ignoring that rule and using the z-score if it's a big sample size. Okay, so to assess the accuracy of a laboratory scale, a few guys were a little confused by the wording on this particular problem. I appreciate that. It's kind of a little bit offbeat. Okay, let me move this out of the way and get back to this. Okay, good. Okay, to assess the accuracy of a laboratory scale, a standard weight that is known to weigh exactly 1 gram is repeatedly weighed 25 times. How many of you guys have had the experience of getting up in the morning and measuring your weight and getting on the scale, and the scale, you read the scale, and I'm going to say we're all skinny, and we get on scale and we weigh 120 pounds, right? You get off the scale and you say to yourself, well, did I just read that right? Was that 120 pounds? You get back on there, you weigh yourself again. This time it's 119. You get back off the scale, you get back on there, and this time it's 121. Usually, if you got digital scales, it'll just fall on a number and stick with it, right? That's when a measurement is the same every time you do it, that's called a precise measurement. When it's accurate, when the measurement is the actual real value. In other words, just because it says 120 every time you step on and off of it, it means the measurement is precise, it's repeatable, but it doesn't mean it's accurate. In other words, perhaps you weigh 125, but it's reading 120 every time you get on and off. Accuracy is whether or not scale actually reads the real value. So in this case, we're measuring the real value. Now, on a laboratory scale, we're measuring very, very, very tiny quantities of weight. So it's not unusual to put something on the scale and read it, and it'll say 1.00019. And then take it off, put it back on the scale, say 1.00017. And then put it back in 1.00022 or something like that for us to get variable readings. And it's not unusual for you environmental occupational health majors to, if you're weighing a filter or something like that, and you're going to reweigh it afterwards, that you might take several readings and average them so that to get the best guess on what the most accurate guess on what the actual weight, most accurate weight is of the thing. So that's what we're doing here. We're taking a 1 gram weight that is, it's a standard weight. It's known to be exactly 1 gram. And we're putting it on this laboratory scale. We're putting on this laboratory scale in order to test to see if it's really accurate, if it's correctly reading 1 gram when you have 1 gram weight on there. So let's see how this is going to work. We're going to put that 1 gram weight on there. It's known to be 1 gram. And we're going to put it on there 25 times. So we're going to get 25 readings. Some of them are going to be the same, some are going to be different. The resulting measurements, the average weight is 1.05. Well, we averaged it and it came out to be more than 1 gram. However, it would have been very unusual for us to get exactly 1 gram, super, super precisely. So maybe that's not so unusual. Maybe you got that 1.05 because just by chance, because we're bound to be either exactly there or a little below or a little bit above. So maybe we got that by chance. And now we're going to say to ourselves, well, what's the likelihood? Well, based on taking 25 measurements and getting an average of 1.05, what's my 95% confidence interval for the true weight of this object, which I know really is 1 gram, that I put on there? What's my 95% confidence interval for what this scale would read if I just kept doing this, thousands of times. Okay, so we're going to calculate a confidence interval. X bar is 1.05, and sample size is 25. And the manufacturer tells you that standard deviation of repeated weights on this kind of scale is 0.010. In other words, that's our population standard deviation for all these if repeated times we would have done this. Okay, so now we know sigma because the manufacturer told us sigma, right? If we hadn't known sigma and this was based on our sample size, would we use the z-score or the t-score in this case? Remember, what's the determinant that we'd use the t-score, right? Exactly. And why would we use the t-score? We would use the t-score because we didn't know the population standard deviation, and it's a small sample size. Exactly right. This is exactly the kind of situation we would use the t-score. Okay, in this case, though, we're not going to use the t-score because they told us that we know the population standard deviation, so we're going to use the z-score. Okay, so, and if you want, as an exercise, you could recalculate it again. In fact, we might, maybe we don't have to. Okay, so I'm going to go here. Okay, so I'm going to go ahead and do this. Okay, so we want to know what our 95% confidence interval is. So our 95% confidence interval is going to be, well, I need standard error first. So standard error is going to be 0.010 over the square root of the sample size, which is 5. Okay, so that's going to be equal to 0.002, right? So that's going to be our standard error. So our confidence interval is going to be 1.005 plus or minus 1.96. And if we hadn't made that assumption, our standard error would have gone to the table, 24 degrees of freedom, and it would have been something like 2.02 or something like that. One times our standard error, which is 0.002. Okay, so I'm going to go ahead and resolve this margin of error and get my calculator. So clear 1.96 times 0.002, and that's my margin of error. Clear, and I'll put it in there. I'll clear this, and it's 1.005 minus our margin of error, leaves 1.001. Okay, and I'll add another. I'm going to make it 1.1. Right? I'll round that off that 08 to 1.1. Okay, that's our lower limit, and our upper limit is going to be 1.005 plus our margin of error is going to be 1.0089. Okay, so we're 95% sure that the real average, the true average, if we use this scale over and over and over again, thousands and thousands of times, that the true average would be between 1.011 and 1.0089. Okay, so let's take a look at the next question I have here. Can you state with 95% confidence that this scale is not measuring the 1 gram weight correctly? Well, in fact, we're 95% sure that it's measuring the 1 gram weight on the high side. Okay, and why is that? Because 1.0000 is outside of my confidence interval. So I'd say to myself, boy, it really looks like that we have a high level of confidence, like 95% confidence, that it's not reading 1 gram correctly. Now, had we gotten a confidence interval of 0.9990 to 1.0010, if that had been our confidence interval, well, then our 1 gram would have been within that confidence interval. So we wouldn't have been able to say with 95% certainty that what we're measuring, the mean of that, the true mean is of the whole population of measurements, is really going to be different. So in a sense, this is kind of like doing a t-test that we started to do this week. In reality, statisticians, we can kind of like do this way because there's only a single sample, that we're dealing with, and we're comparing it to a fixed value of 1.000. So it really kind of works very similar to the way that our t-test would work. But in general, statisticians don't like to use the confidence interval in this manner. The real purpose of the confidence interval is to tell you what the range that you can expect the true population mean to be within, not really to use that to compare it to other confidence intervals or other values. For that you really use the t-test, what's the stuff we're going to learn later, like analysis of variance and so on and so forth. We're going to use other tests for that. So confidence interval, even though we can kind of get away with it using it in this sense because it's only a single value, a single sample t-test of a fixed value compared to a mean first sample, we can kind of get away with it. Normally, we don't like to do that. We really have other ways to do that. And you guys have already started to learn those other ways. So in fact, the answer to B would be, yeah, it really looks like, for our purposes, it looks like, yeah, we can say that the scale seems to be reading high because the entire confidence interval is above 1. Okay, so we're 95% sure that the true weight that the scale thinks that this thing is more than 1. Okay, so let's take a look at the next one. Researchers examined the 1999 to 2000 National Health and Nutrition Examination Survey. NHANES, we might actually be pulling data from this this annual national survey to estimate dietary intake of 10 key ingredients by study participants. One of those ingredients was calcium. The intake was measured in milligrams for adults 16 years and older. They found a mean daily intake of 721 milligrams, but there was a lot of variability and a standard deviation of 454 milligrams. Use these values for the mean and standard deviation for the U.S. population. By the way, this is a very large study. There's a lot of participants in this study. Okay, so we're